that's hot. Jeez. All right, something fun to play with today. Solid state is the next leap in lithium battery technology. Renogy is moving into that space with this really nice, slim, semi-solid state battery, and it comes with some impressive characteristics, particularly in their low temperature capability. This is an impressive package. It is super solid, totally waterproof, very thin. This would be a great solution for off-road vehicles. Renogy sent me 4 of these batteries so I can show you a 12 volt, 24 volt, and 48 volt configuration. And I can tell you there's a dramatic difference between the configurations. And I have got some great torture tests for this thing. So welcome back to Projects with Everyday Dave. Let's do some testing. Before we dig into the testing, let me go over some of the unique characteristics of this battery. It has a compact, robust, sealed form factor with an IP67 protection rating. That means it can be immersed in water up to 1 meter deep for 30 minutes. Now, I wouldn't recommend doing that, but at least you can have some confidence that if it gets a little wet or something, it's not going to be destroyed. It has mounting features right on the side of the battery. You can get brackets that allow you to mount it directly to a surface, and similar brackets that allow you to stack multiple batteries together really easily. It's rated for a 200 amp continuous discharge with an 8-year warranty and 6,000 cycles with an 80% depth of discharge. But I really think the best feature for these solid state type of batteries is the low temperature performance. Most lithium batteries on the market cannot be charged below freezing. And this one can be discharged down to -4 degrees Fahrenheit or -20 Celsius and charged down to 14 degrees Fahrenheit or -10 degrees Celsius. Now, the charging rate has to be reduced to 0.1 C, so about 10.4 amps with one battery, or if you're running 4 in parallel, a max of 41.6 amps. But at least you're not wasting energy from the battery to run battery heaters to warm it up or wait for the temperature to come up before you can use them. On top of all that, it has Bluetooth and CAN communication. If this battery can live up to those specs, it's going to be a hard one to beat. For a small 12 volt system, you would be able to use just one of these batteries. And I'll run a few tests here with the Renogy 2000 watt inverter with some typical tools and household appliances, and they should all be no issue. So let's give that a shot. We'll start with a little coffee. Something everybody needs to do off grid. Starting to heat up the water, pulling 125 amps. These things draw a lot of power, 1500 watts. And that's why you want at least a 2000 watt inverter. Much less than that, and you're just pushing the limits of your inverter all the time. The current kicks right back up as soon as we start to brew, then it's got to heat the water for the next round. Ooh, that's hot. There we go, as expected, no problems heating up some water, even with just one battery. All right, we have a few things that might actually draw a little bit of a surge. The microwave is one of those. So I'm going to use a current meter set to inrush. We'll be able to measure the maximum amount of current it pulls right at startup. All right, I have a cup of cold water. Let's heat it up. The inrush actually wasn't as high as I thought. It was only 47 amps. The running current's higher than that at about 105, but still less than the coffee pot. Microwave runs fine, no issues. Battery doesn't even care. We're nowhere near its limit. All right. Whew, and it's hot. Yep. Microwave is no problem. Let's try a couple power tools, and that'll wrap up the one battery test. Now I have a pancake air compressor and a shop vac. I'm going to check the inrush current when I turn this on. Should be a big surge. 180 amps, that's a pretty big surge. That's why you need a little larger inverter and a robust battery. If you want to run some of the induction motor type power tools, they have a big startup current. Even this small pancake compressor, it took almost 200 amps to get it rolling, even though the running current wasn't that high. Let's see what the shop vac does. That's even more, 225 amps just to get that motor started. That is not a small draw. Just out of curiosity, let's see how much it takes to run the compressor and then start the shop vac at the same time. Well, I can't do inrush with two loads that start independent, but let's just see what the total current draw is and see if it can actually start it up. Okay. All right, we were over 250 amps there, and the inverter did not want to run a long time at that load, but I was able to start up the compressor and the shop vac at the same time. It was over 250 amps on the meter. I don't think the shunt could pick it up that fast. The battery didn't care at all. I think if we want to try and find the limits of just one battery, I'm going to have to add another inverter here so I can boost this load. I don't have a 3,000 watt inverter on hand, but I guess I could plug 2 inverters into it and see what the total is. All right, I plugged in a 1,000 watt and a 2,000 watt Renogy so we can put a load on each one and see if we can push this battery past its 200 amp continuous max. Renogy didn't provide these inverters. I bought them both myself for previous projects, just in case you're wondering. I also have an amp meter here, so I have a couple sources of current so I can make sure that we're capturing exactly what happens. All right, let's start it up and see what happens. All right, looks like the BMS tripped. All right, we were 230 amps with the clamp meter. I don't know if you could see that in the screen or not. The Victron shunt was showing a little bit less than that, but either way, we were well over the 200 amp continuous running max for the battery BMS. I think with the compressor running and starting up the shop vac, that surge current, which is really high, tripped the BMS because everything shut down for a second, but then it came back on and kicked them both on at the same time and ran them continuously. I did get a warning on the app for the battery that said we were over current, but it kept chugging along anyway, and it also added a warning for under voltage because the battery capacity is getting a little low. We're getting towards the lower voltage range for the battery. Either way, I mean, I was able to run a 2,000 watt and a 1,000 watt inverter at pretty high loads, pulling over the maximum continuous output for this battery, and it chugged right along. I'm pretty impressed with this battery. Just one unit by itself can really do a lot. It's not the cheapest battery, but maybe this is a case where you actually get what you pay for. Well, just running a few appliances, you can see pulls a tremendous amount of current, over 200 amps. Now let's take a look when we switch from 12 volts to 48 volts, a complete difference in the amount of current that's drawn to put out the same amount of power. I'm going to hook this up to a 8,000 watt 48 volt inverter and we'll see what we can do with it. We'll only have 200 amps available when you put these in series. Even though I'm going to put 4 of them in series, you're limited to the minimum amperage of one battery. When we put 4 of these in parallel for 12 volts, we get 800 amps, but you'll see at 48 volts we don't need all that current, which means smaller cables, a lot less stress on the joints. So let's check that one out. All right, it's 48 volt time. I've stacked 4 of these 12 volt batteries together and connected them in series by alternating them upside down every other one. I can connect them with 3 short bus bars, giving us our positive off this terminal, and then in series we work our way back to the negative post at the top battery. Now I'm coming off of these posts into my Victron monitoring setup so that I can get some very accurate details on the amount of current that's being pulled through the system. But I could just connect this directly to my EG412K PV because it has its own breaker that I can easily disconnect these batteries if I need to. I bought this inverter from Signature Solar almost a year ago to expand my solar system, and I've had no issues since I installed it. I'll include links to the install and any discounts I can provide in the description below. This system does have the ability for communication depending on which batteries you're using. We're just going to use the manual mode to manage this battery. From the monitor page, I click on maintenance, then I use the old setting page and click on read to bring in the current values. If I were installing a battery with established communication, I would select lithium and the corresponding communication protocol. For any other lithium iron phosphate battery, or in this case, our Renogy setup, I can use the user mode, which is labeled lead acid in the setup menu, but you can use it for any custom profile. When you click set model, the inverter will restart, so be prepared for that. The spec sheet calls out a boost or charge voltage of 14.4 volts, and we have 4 in series, which would be 57.6 volts. For the inverter, this is the absorbed voltage, and I'll set that to 56.2, which is equivalent to about 3.5 volts at the cell level. And that should give us some margin for when the individual batteries are not in the exact same charge state. I don't want to overcharge one of them and have it shut down, disconnecting my series setup. I set the float voltage to 54 volts so that once the battery is fully charged, it won't hold it at a higher charge voltage or constantly run a charge cycle. Dropping down to the charge settings, we'll be using voltage instead of state of charge since we don't have communication with this battery. I set the charge current limit to 50 amps, which is 0.5 C for this battery, and that is the recommended charging rate. Of course, this inverter can deliver way more than that, so we need to make sure and limit it. In my case, I have AC charge disabled, so it will only charge the batteries from solar. And in backup mode, I've enabled PV charge priority and set that limit to 2.5 kilowatts to maintain that recommended 50 amp or half C charge rate. For PV charging, I just set my inverter max charge voltage to 56.2 volts. And we're done with charge settings. For the discharge setting, I'll once again use voltage instead of state of charge to set the discharge current limit to 162 amps for this inverter. Now these can put out 200 amps. If I had a 10,000 watt inverter, I could set it a little bit higher. And now for the end of discharge voltage. The BMS limit is 10 volts, and that's when it'll shut down. 4 times 10 is 40 volts, but there's very little capacity below 48 volts. So I can set the pack to a minimum of 48 volts to reduce stress on the battery and still use 95% of the battery capacity. And that's all the settings we need to allow us to run with this inverter. I top balanced each one of these batteries individually with 14.4 volts to get them all to 100%. They have CAN communication that's supposed to allow them to talk to each other for balancing during charging, but it might need a Renogy controller to do that. I wasn't able to get it to work by just connecting the batteries to each other, so I'm going to rely on top balancing for now. If I was running this for a long period of time, I would have to come back and top balance them on occasion because eventually they would get out of sync. I've been running this for a couple of days now. Here's some results on this graph. The battery's charged with solar during the day and then supported my refrigerator and 4-ton AC unit throughout the night. You can see it pulls over 2 kilowatts periodically, completely dwarfing the fridge consumption. By morning, when the sun came out, the batteries were down to about 37% and still almost completely in sync. That combined 5.3 kilowatt hour capacity is enough to run a lot of emergency systems. I mean, it's even running my 4-ton ACs, so that's pretty nice. Now with the 12 volt setup, we were pulling over 200 amps from the battery to support only a 2500 watt load. Now, when I put these in series, I still only have 200 amps available, but at 51 volts, that can put out a continuous 10,200 watts. At 12 volts, we were overloading the BMS at only 2500 watts. The inverter can easily export 8 kilowatts, and that's sufficient for my standard level 2 EV charger. Now, the combined capacity of these batteries being 5.3 kilowatt hours and a typical EV performance of 3 miles per kilowatt hour, if we drain these batteries into the EV, that would extend our range by about 15 miles. Not a tremendous amount, but in an emergency, that might get you to the store or to the hospital if you needed to. So let's do a quick export at 8 kilowatts and see what the current draw is and how it performs. I can just go in the EG4 settings and set 8 kilowatts of export to the grid and turn it on. All right, the fans are howling, the inverter is maxed out, and the Victron app shows we're only pulling 163 amps. I mean, these things aren't even breaking a sweat. That is the beauty of a 48 volt system. You can get so much more power at a much lower current. That allows you to use smaller cables and reduces a lot of other expenses and load on the hardware. You can see on the Renogy app, each individual battery is putting out over 160 amps, which correlates pretty well with the 160 amps that our Victron meter is showing. The capacity is staying really well balanced, the load on each cell is really well balanced, and we could probably improve it a little bit with a little bit larger bus bars, but all in all, I mean, this is working pretty well. I'll run these for a while, but I mean, they're completely cold to the touch. They're gonna have no problem maintaining this load indefinitely. You can see the terminals starting to get a little bit warm there. These bus bars are probably slightly undersized. I just used ones that I had randomly available. That's the nice thing about using the infrared camera. You can see if there's any hot spots in your system. Maybe a bolt wasn't properly tightened. You can make an adjustment so you don't have a problem later on. Cables themselves are just barely warm, a little over 100 degrees. This post is way cooler. It tells me maybe that one has insufficient torque. Something going on there. Could be that this isn't clamped properly. This is a 1-aught cable. You can see how much significantly warmer that one is. That's a great way to check on your system. So can I charge an EV? Yes, I can. But what is the most we can do with 12 volts? Now, if I stack all 4 of these batteries together and connect them in parallel, I could get 800 amps available at 12 volts. And I'm thinking, what could I do with 800 amps? I wonder if I could weld with these. Just make some welding cables, connect them directly to the batteries, and see if I can stick weld with these. I know you want to know if I could do it too, so let's try it. Okay, maybe I just wanted an excuse to buy some really nice heavy-duty copper bus bar material and a giant DC breaker, because who doesn't want a 400 amp DC breaker? Plus some welding rod and welding cable materials. Of course, none of this was in the budget for this video, so if you want to encourage more irrational behavior like this, consider adding a super thanks down below. I really appreciate it. There's a lot of copper here, and I don't really want it to go to waste. I feel like I should collect it for another project or recycle or something, so I've got a pot here. Just don't tell my wife. I think this will work. The giant strips of aluminum is really satisfying. I don't think my pot is actually capturing that much. All right, I think I probably saved, 1 or 2 pennies worth of copper there. That was totally worth it. Of course, don't do this at home. I think I'm supposed to say that, right? If this bar were to touch across these terminals, especially once I get them all connected, I'll have over 800 amps, quite a bit over 800 amps available. That would not be a pretty sight. Of course, if I do it on accident, you'll get to see some really pretty sparks. I should probably have safety glasses on. There, I feel safer already. All right, let's see what we have. 13.3 volts. Seems like a low voltage, and of course it is, but the amount of current behind it is pretty significant. So if I were to touch something metal across there, we would have a big spark shower. But 12 volts, not a big deal for the human hands. Interesting how electricity works. Yeah, I don't think that this handle was meant to hold a 2-aught cable, but by golly, I got it in there. No one can complain I didn't have a big enough cable. All right, I made my cables. Now I just need to connect it up. I put my 400 amp breaker mounted to the table there securely so that I can control when the power is going to be available. So let's connect up our power cords. These bus bars are 1/4 inch thick. They should perfectly distribute the load between the batteries, but I'll still put the positive at one corner and the negative at the other. Nothing left to do but try and weld something. After all this, it's going to be really disappointing if the BMS detects a short circuit and just shuts off. But after all this, I'm going to have to put it in the video anyway. I'm no welding expert, so feel free to leave any advice in the comments you like. Here we go. Whoa! Did not expect that. Must have gotten that rod hot. Look at that rod! The whole rod is glowing red. Wow! It's melting the rod. Whoa, that's hot! What current was that? $250 amps. Jeez. Okay. Clearly the voltage is a problem. I mean, this rod is melting. I'm putting over 250 amps through it. The batteries are chugging along no problem, but I have completely melted the welding rod. I mean, it was glowing, the whole thing. So the problem here is we can't weld at that low of a voltage. So if I want to weld, I'm going to have to raise the voltage. I can break this stack into two. Clearly the current isn't our biggest problem, it's the voltage. So I'm not going to need these huge bus bars to achieve that. I think I can put two in parallel and then those two in series, and we can get 24 volts at 400 amps. Oh. Let's do it. All right, I reconfigured my battery. I took the top two, turned them upside down. So I have two in parallel on the bottom, negative poles connected, two in parallel on the top with the negative poles connected. So I'm able to use one bus bar up the back side of both of those. And then on this side, I didn't want to cut my big, beautiful bus bar in half. So you can hate me if you want to, but I'm just connecting the top two with that bus bar. And then I have two cables connected to the positive terminals connected together at my breaker, so that, because I didn't have another chunk of bus bar for that, so that should work just fine. That gives us 24 volts plus 26, almost 27 volts across these two poles. And according to ChatGPT, that should give me a much better chance. And it also recommended some 16th inch rod. I was trying 1/8 inch before. And it's not just the thickness of the rod, but we need enough voltage to make an arc. And 12 volts just isn't enough to get an arc. We can get some sparks and we can melt the rods. There's plenty of current available, but we need more voltage for an arc. So if this doesn't work, the next step would be to go to 48 volts. And I probably should have tried that while I had the 48 volt configuration, but I was worried about the BMS recognizing a short circuit and disconnecting. Hopefully this 24 volt version will work. All right, well, that was much closer. The 24 volt configuration was able to put down a few little beads of weld there, so it is possible. I think with enough skill you could probably do some tack welding, maybe even a little bit of welding if you had the capability to hold that arc distance just perfectly. So I want to say 24 volts is possible, but not really very usable. But now I'm kind of curious if, I mean, the batteries don't seem to have any problem holding the current. If I put it in a 48 volt configuration, I wonder if I could actually get it to work. And as much as I don't want to reconfigure these again, I know you want to know and I want to know if it can do it with 48 volts. So here we go again. I'll reconfigure this to 48 volts and we'll see if we can do that. I should have probably started there. I'm not very happy with Past Dave for not considering the order of operation here, but for you guys with the advantage of snap editing, I've reconfigured this to 48 volts, so we're taking the positive off the bottom, negative off the top, and then these just run in series all the way through, just like before. All right, let's give it a shot. Now we're not actually 48 volts, we'll be 50 some volts here. Okay, totally melted my rod, but we have plenty of arc now. And I think herein lies the problem with this kind of a situation. You can't control the voltage and current. It's going to give you everything that the rod wants. On a regular welding machine, you can dial in the voltage and current. So you have to pick a rod that's going to exactly work with this. And the 16th inch rod, we could get a little bit of welding at 24 volts. I'll try the 1/8 inch rod. All right, 50 volts and 1/8 inch. Let's see what we can do here. Well, I think that shorted it out. Okay, as soon as I touch it, It does exactly what I thought would happen. It senses short circuit and trips the BMS. It immediately restarts. I mean, I have 53 volts available now, but that 1/8 inch rod carries just way too much current. And we saw that at the 12 volt configuration. We had 250 amps. And now with 50 volts, I guess I'd have to calculate what the resistance is in that wire to tell us what kind of current we're actually seeing there. I could probably put this on inrush and see if I can pick up how much it's actually registering. It's only showing 105 amps, but it's probably actually a little bit sharper in that. It's probably a very sharp ramp up, and the BMS is designed to pick up those very sharp spikes as a short circuit. And that's what it should do. You want it to immediately shut down if there's a short circuit. You know, it's not really configured to be a welder. So what have we learned here? 24 volt configuration with the 2 batteries in parallel is the closest you're going to get to being able to weld. The 12 volt configuration with 800 plus amps available will melt rod, no problem. But it's just not enough voltage to create an arc. I think if we had 8 of these batteries, we could put 2P4S and we would probably be able to do 50 volt welding. But even then, you just can't dial in the precise voltage and current that you want to work with, so it makes it really hard to weld. In an emergency situation, I guess 24 volts, 1/16 inch 6011 with 24 volts and 2P configuration was as close as we were able to get to actually doing a usable weld, and even that was pretty sketchy. But that was kind of a fun experiment. Now we know what these batteries can do and a little bit more information about emergency welding, if that's important. All right, let's pull everything together. We have covered a lot of ground with these batteries today, and I think you have a pretty good idea of what they can and can't do. So let's look at what is the ideal application for these batteries and how much do they cost. These batteries aren't cheap. They're $750 a piece, or if you buy 4 of them, they're $712 a piece. So when would it make sense to purchase these batteries? Well, there's 3 key features that these batteries uniquely offer that might make sense for you to spend the extra money. 1, the ability to charge them in sub-freezing temperatures without wasting any energy to heat your batteries. 2, they offer higher level of durability with the IP67 rating and really robust case. You can have some confidence that you're not going to have a problem with them in your off-road vehicle. Finally, the slim form factor provides unique packaging opportunities if you have limited space. If you are interested in purchasing one of these batteries, there are additional discounts that Renogy has made available for my viewers, and you can find those in the link below. Or you can find them on my website, projectswithdave.com, where you can find all kinds of other resources and discounts. The offer that's available right now is an additional 5% off, so that's pretty good. If you're looking for an inverter for your 12 volt system, watch this video right here. I compare 7 2000 watt inverters, including the Renogy 2000 watt inverter, so you can see what inverter is best for your budget and your application. Or dig into more off-grid solutions with this video right here. I have more fun videos coming up soon, so be sure and subscribe, and I'll see you next time.